Hi, I am Shahnawaz. In this lecture we will introduce degree sequences and then we'll prove the Wang-Kleithman theorem. So we'll start with the definition of degree sequences. So let us define a degree sequence. So let di where 1 is less or equal to I is less or equal to n be the degrees of vertices, be the degrees of vertices vi of a graph G, of a graph in any order. Then the sequence, this sequence di where this I runs from 1 to n is called the degree sequence of the graph, is called the degree sequence of the graph. Conversely, if we consider a sequence of non-negative integers, let di where this I runs from 1 to n be a non-negative sequence of integers. Then this sequence is degree sequence if it is a degree sequence of some graph. So this di, let's denote this sequence by d. Then d is degree sequence if d is degree sequence of some graph. Degree sequence of some graph, and that graph is set to realize this sequence D. And the graph is set to realize the sequence. Let's consider the example. So let G be the graph, is given like this. So here this is a vertex. So this is a graph with 6 vertices. So then sequence. Now the vertex and degree of this vertex is 0, degree of this vertex is 2, and degree of these two vertices is also 2. So 2 appears 3 times, and the degree of these two vertices is 3 and 3. So this is the degree sequence of this graph. Now if we consider another sequence, so given this graph G, this is its associated degree sequence. So there is a one-on correspondence between corresponding to each graph. There is it is unique degree sequence. So this degree sequence is unique. Now let us consider another sequence of non-negative integers. So let us suppose we have this sequence 2 2 3 3 and 4 4. Now there is a question whether this sequence is a degree sequence of some graph or not. Now in this case this happens to be a degree sequence of some graph, and this sequence is set to, and the graph is set to realize this sequence, and such a graph is given as note that this graph has 6 vertices as which are same as the number of elements in this sequence. Now this vertex, now these two vertices are of degree 3 and 3, these two vertices are of degree 2 and 2, and these two vertices are of degree 4 and 4. Now let us define the laying of let d is equal to di, where r runs from 1 to n, be a non-negative sequence, be a non-negative sequence, and k be any integer, this little k be any integer between between 1 and n. Let d prime be the another sequence of same length, so di prime contains the element these little di primes. This is a sequence, be the sequence obtained from d, obtained from d, capital D, by setting dk equal to 0 and di prime to be equal to di minus 1. So this is true for all this is true for largest dk elements of d other than dk. Then in this case, then d prime is called a residual sequence of d, residual sequence of d by laying of dk. Now let us do an example here. Let d be the sequence 2 2 3 3 4 4. Now in this sequence, this is d1, this is d2, this is d3, d4, d5 and d6. Now let us take k equal to 5. Okay, is equal to 5. Now we have to form the residual sequence d prime by setting d5 to be equal to 0, and now we have to look over the largest d5 elements of this sequence d. Now d5 is equal to 4. Now we have to look 4 largest elements of this sequence other than this 4 itself. So the largest 4 elements of this sequence other than this 4 are one is this element, this is second, this is third, this is fourth. Now for these 4 elements we have to subtract 1. So this is 1, this is 2, this is 2, this is 0, this is 3, and this is same as 2. So this is the residual sequence by laying of d5. Similarly, let us keep this d1 prime. Now d2 prime, if we lay off suppose d3, so if we lay off d3, so d3 becomes 0. Now we have to look over largest d3 elements of this sequence other than d3. Now here d3 is 3, so we have to look over largest 3 elements of this sequence other than this 3. So these largest 3 elements other than 3 are, one is this 3, this is second, this is third. So for these 3 terms we have to subtract 1. So this is 2 here, this is 3, this is 3, and these 2 elements are as it is in the original sequence. So this is the residual sequence obtained by laying of d3. Now if v1 v2 through v and b the vertices of the graph corresponding to the degrees d1 so on dn, then so let us make it another definition. Let hk be the graph obtained on the vertex set say v1 through v1 by joining vk to tk vertices. Now when we lay off dk here and this sequence, so dk becomes 0. Now corresponding to dk, now dk equal to 0 means the vertex vk has degree 0. So these are the vertices. Suppose now first we'll define, then we do some examples to make it clear. So by joining vk to dk vertices, by joining vk to dk vertices, corresponding to the dk elements, dk elements obtained in d prime after laying off dk in d. Now d prime and d have their usual meaning. So d prime, so this d is di where I runs from 1 to n. So this is 1 to n. So what does this mean? So if we consider this example over here, so this is the example. So this is over d 2 2 3 3 4 4. Now this is the degree of vertex v1, which is d1, this is d2, this is d3, this is d4, this is d5, d6. Now these are the vertices of degree v1, v2, v3, v4, v5, v6. Now when we lay off d3, the residual sequence d prime is 2 2 0 2 3 3. So then h3 will be, so we have to, this is the graph on the vertex set v1 through v6. So this v3 here has degree 0. So now this v3 we have to make it adjacent to the vertices whose degree is changed after laying off. Now the vertices whose degree is same is v1 and v2, and the vertices whose degree is altered is v4, v5, v6. So we have to join this v3 because this is the vertex which whose degree we laid off and during the laying off operation. So v3 must be adjacent to v6, v5 and v4. So this is the graph h3, and this h3 is called HK is the subgraph obtained by laying off. This is, and this subgraph is obtained by laying off dk. Now let us proceed to prove the Wang-Kleithman theorem. So this is a theorem by Wang-Kleithman. Now the statement of this theorem is like this. It states that a non-negative sequence is degree sequence if and only if the residual sequence obtained by laying off any non-zero element of the sequence is degree sequence. So a non-negative sequence is a degree sequence is a degree sequence if and only if the residual sequence obtained after laying off any non-zero element. Any non-zero element of this sequence is the degree sequence. Is a degree sequence. Is a degree sequence. So let us prove this. Let us consider a non-negative sequence. Consider a non-negative sequence. Say D is called di, where I runs from 1 to n. Let d prime equal to a double di prime where I runs from 1 to n be the residual sequence obtained from D after laying off dk, where this dk is non-zero and this k is lying between 1 and n. So first we assume d prime is degree sequence and we show d is the degree sequence. Suppose d prime is a degree sequence. Now we need to prove d is a degree sequence as well. Now if d prime is a degree sequence, then there is some graph g which realizes this d prime. Therefore there exists a graph g which realize d. D prime. Let us name this graph as g prime. Since dk is 0, the corresponding vertex corresponding vertex vk in G prime has degree 0. And some dk vertices, say dij, where this j runs from 1 to dk. So these, let us name these vertices as Vij. Some dk vertices, say Vij, has degree, have degree, so their degree is dij minus 1. Now if we join this vertex vk to all the vertices Vij, now join vk to all these vertices, we get a graph say G whose degree sequence is, now since this vk is of degree 0 in G prime, so in G its degree will be k, because this vk is adjacent to these k vertices, and these dk vertices, their degree is going to exceed by 1 because vk is adjacent to each of these vertices. So the resulting graph will be a graph whose degree sequence is d. Hence we are done. That is, we have proved that d is graphable. I mean G realizes this sequence d. We get a graph, say G, whose degree sequence is d. Let's understand this half portion with an example. So first we considered the sequence d. Now to be concrete, let d be the sequence 2 2 3 3 4 4. This is d1 d2 d3 d4 d5 and d6. This is the degree of vertex v1 v2 v3 v4 v5 v6. Then what we did, we obtain the residual sequence d prime by laying off some non-zero entry. So here in this case we lay off, say, d3. So by laying off d3 means, first of all, d3 will be 0, and the largest d3 vertices, that is the largest d3 elements of the sequence, that is the largest 3 elements of the sequence, they are 3 4 4. So their degree becomes 1 less than it is in the D. So this becomes 2 here, this becomes 3, this becomes 3, and this is 2 and 2 here. So this is the required sequence, required residual sequence. So in this part we assume that this the residual sequence is graphable, and we proved that this sequence D is also graphable. So this is obviously graphable because for this sequence we have this graph. This is the degree of V1, V2, V3, V4, V5 and V6. So let us first draw this. V5, V6. So first of all let us draw its graph. So this is the vertex V3 because its degree is 0. Then we have three vertices of degree 2. So this is V1, this is V2, this is V3, this is V4, this is not V4, this is V1, this is V2, this is V4 here, this is V5, this is V6. So D prime is obviously graphable. Now to make D graphable we have to join this vertex, I mean the vertex corresponding to the element which we laid off, that is D3. We have to join this vertex to the largest 3 entries, and that is V4, V5 and V6. So we have to join this vertex and let us keep this V1, this V2 and this V4. So this is V1, V2, V4. So if we join this V3 to V4, V5 and V6, now the degree sequence for this graph is, so here the degree is 2, here the degree is 2, so 2, 2. Then we have degree 3, 3 because V3 and V4 have degree 3 and 3. And finally V5 and V6 have degree 4 and 4, which is this sequence. So this sequence is the degree sequence of this graph. That means this is the degree sequence. So this is example to understand the first part. Now conversely, suppose D is a degree sequence. We shall prove that D prime is a degree sequence. Let S be the set of vertices, corresponding to the DK largest elements of corresponding to the DK largest elements of D minus VK. So in this case the vertex, the entry which we laid off is D3. So over vertex will be v3, and the set S is a set of vertices which correspond to the largest D3 entries, that is 3 entries of D. So the largest 3 entries of D are 3, 4, 4. Now corresponding to 3, 4, 4, the corresponding vertices are v4, v5, v6. So in this case, this set S contains the vertices v4, v5 and v6. Note that this vk is the vertex which is laid off. Now what we do, we claim that there is a graph realizing D. We claim that there is a graph realizing D in which Vk is adjacent to all vertices in S. So this is our claim. Now suppose this claim is not true. Now what does that mean? Suppose not. I mean that this claim is not true. If this claim is not true, then G be a graph, then let G be a, suppose this is not true, and let G be a graph realizing D such that Vk is not adjacent to all but a maximum possible number of vertices. Maximum possible number of vertices in S. So what we assume here is that we assume G to be the graph which realizes D such that this vertex Vk is not adjacent to all the vertices in S, but Vk is adjacent to the maximum possible number of vertices in S. So if Vk is not adjacent to the all vertices in S, so there must exist a vertex outside S to which Vk is adjacent. So suppose this is Vk here, and this is the set of vertices in S. So what we assume Vk is not adjacent to all the vertices here. So there must exist vertex, say, and let us name it Vi, to which Vk is not adjacent. Now by drawing this dotted line, I mean Vk is not adjacent to Vi. Now Vk is the vertex whose degree is, so suppose Vi belongs to S such that Vk is not adjacent to Vi. So let us choose Vi to be that vertex to which Vk is not adjacent. Now note that Vk, degree of Vk is dk, and dk is same as size of the set S. Now if degree of Vk is S, and here Vk is not adjacent to this vertex, now these are dk vertices here, so that means it is given that to which on Vk there are dk number of edges incident, so there must exist a vertex outside this set, say Vj, such that Vj is adjacent to Vk. So from S, the maximum number of edges adjacent to Vk may be at most dk minus 1, because Vi is not adjacent to Vk. These are dk vertices, and given that Vi is not adjacent to Vk, also it is given that degree of Vk is dk, so there are dk number of edges incident at Vk. So those dk edges will not come from the set S alone, because Vi is not adjacent to Vk. So there must exist a vertex Vj which is adjacent to Vk. Also therefore there exists a vertex, say Vj not in S, such that Vj is adjacent to Vk. Also degree of Vj is less or equal to degree of Vi, because S contains all those vertices whose degree is the largest. So if Vj is outside this set S, so degree of Vj will be less or equal to the minimum degree of these vertices. So now let us see here, at Vj we have edge from Vk, but at Vi we don't have edge from Vk. So to preserve this identity and this inequality here, we must have a vertex, say Vh in G minus Vk, such that Vh is adjacent to Vi but not adjacent to Vj. So we have to make it dotted. So this is an important point here. Had this not been true, then this inequality is not valid, because at Vj Vk contributes to its degree, but at Vi Vk do not contribute to its degree. So it seems that degree of Vi is less than degree of Vj, but it is given that this inequality is true, i.e. the degree of Vi is bigger or equal to degree of Vj. So to make this inequality True, there must exist a vertex VH which is adjacent to Vi such that VH is not adjacent to Vj. Now also this is true, therefore there exists a vertex, there exists a vertex say VH which is adjacent to Vi but not to Vj. Now let us do the following. Let us construct a graph. H by removing these two edges. By removing the edges, Vj Vk and Vi Vh, and let us add these two edges, and by adding Vj Vh and Vi Vk. Now let us see here. So by removing this edge, degree of Vk becomes 1 less, but simultaneously adding this edge, it is degree is increased by 1, so the net degree is unaltered. Similarly here, this edge we are adding and this edge we are removing, so the net degree is preserved. Similarly at this vertex, this edge is being removed and this edge is being added, so the net degree is preserved. Similarly here, this edge is removed, this edge is added. By doing so, degrees of Vi Vj Vk and Vh and Vi Vj Vk and Vh are unaltered. So this means the degree sequence for H is also D. Therefore D is also a degree sequence of H. But note that here this H realizes the degree sequence D, in which one or more vertex, namely Vi of S, is adjacent to Vk than G. And one more vertex, namely one name more vertex of one more vertex, namely vi of s is adjacent to vk then g. So this contradicts this maximal definition. Since we assume here, let G be a graph realizing D such that Vk is not adjacent to all but a maximum possible number of vertices in S. So we construct a graph H which is adjacent to more vertices in S than G is. So this contradicts is the choice of G. This contradicts the choice of G. Hence a contradiction. So this means that this shows that G is the graph realizing D. This shows that G is the graph realizing D, in which Vk is adjacent to all the vertices in S. Now let us look over this graph. Let G prime is equal to G minus Vk. Now we are looking over this graph. Then the degree sequence of this graph is then G prime has, or let us write this, and let us write that in this way. Then the degree sequence D prime, which is the residual sequence. Then the degree sequence of G prime is D prime, which is the residual sequence obtained by laying of G, which is residual sequence obtained by laying of dk. So this proves that D prime is also graphable. This completes the proof.